Hi everyone, thank you for joining. Just before we carry on, I just want to quickly check if you can hear me. So if you can just comment in the chat box that you are able to hear me.
Yeah, I
Oh,
can hear you.
better. Thank you. Thanks everyone. Thank you for confirming. Uh, Yeah, just before we start, I just want to highlight a few things here. So if you are joining us for the first time, so we usually encourage everyone to just quickly go on the settings and just to ensure that they disable all the sounds and the notifications, so you don't get any form of a disturbance when you're trying to listen to the webinar or the session. All right. Welcome. My name is Perry. I'm based in the South African office. Today's webinar, the topic is HVAC system sizing based on computational fluid dynamics. This will be presented by our lecturer here at EIT, Mr. Vijay, who is also a course coordinator in our mechanical engineering program. But just before I hand everything to him, I just want to quickly just highlight just common questions. People want to know about the slides and the recording. Yes, we do provide you with the recording and the slides of this session. So just expect that within 2 business days via email. And yeah, just make sure that you keep checking on your emails, more especially junk folders. And then yeah, we will also provide you with the certificates of attendance. So how it's going to work is at the end of this session, I will be providing you with the link or the QR code that you need to follow in order to complete our short survey form. That's how you request your certificates of attendance. Should you not be able to complete the short survey form, unfortunately, they cannot be able to issue the certificate of attendance. So just make sure that you stick around until the end of the session so I can provide you that link or the QR code. Yeah, just for those who are joining us for the first time, welcome once again. Yeah, just to give you an overview about EIT or who we are. So at EIT, we pride ourselves about specializing in engineering. So as you'll see that our program starts from professional development courses. You go in our diplomas, advanced diplomas, undergraduate, graduate certificates, bachelor's, master's, and our highest level of qualification is our Doctor of Engineering. Yeah, we are industry orientated. I always tell people that time and time the technology is changing, the industry is changing. So at EIT, we ensure that our resources and our materials are always up to date to ensure that we keep up with the trends or the market. Yes, our qualifications are created, so we are just like any higher education provider in Australia. Our qualification are created with Australian government taxa, and we also have some of our programs that are recognized under 3 international engineering accords. And yeah, we source our lectures from different parts of the globe. We use very, unique method of delivering our programs. They use live interactive webinars. They use simulations and remote labs. So yeah, just that was just a little bit of an overview about who we are. And then at this moment, I will then hand things to Mr. Vijay. Mr. Vijay, you can take it away, sir. Thank you.
Yep. Thank you so much for the lovely introduction, Mr. Berry. So, hello everyone, and welcome to this webinar. My name is Vijay Kumar Veera, and I'm a qualified aerospace engineer with about 12 years of experience in using the computational fluid dynamic methodologies for simulating both industrial and academic scale problems. So my degrees are from University of Cambridge in the UK, my MPhil degree, and I have an MTech and a BTech degree from Indian Institute of Technology in Bombay and Madras respectively. So my specialization is in understanding and capturing fluid flow phenomena using computational methods. I have 7 years of experience working in Australia, about 3 years in UK, and about a couple of years in India. And I've worked with a few organizations, as you can see here. So in my current role with EIT, I'm a unit lecturer and a course coordinator in the mechanical engineering department, and I have helped develop lecture materials for teaching advanced fluid dynamics and the introduction to aerodynamics units. And this is for students who are pursuing their masters of mechanical engineering from EIT. So I do have a passion for teaching, so hopefully you'll enjoy this session and also learn some interesting ways of using computational fluid dynamics to solve everyday problems. So that's a bit about me, and I'll just jump into the lecture and the problem statement. So here is an example of a two-bedroom apartment, and if you've been in any apartments, you'll see that most of these apartments need their own HVAC system, so like an AC air conditioning system to control the temperature or the climate within the apartment. And the reason is uh, not, these apartments are not the most ventilated, so you don't instead of relying on natural ventilation, we'll have to use these systems. So the problem statement is to conduct a CFD analysis of a typical apartment, and in that we include typical sources of heat such as electronic appliances, desktop computers, fridges, etc. So assume heat flux, reasonable heat generation from those appliances, and then see how so air moves for in response to changes in pressure and also changes in temperature. So if and the idea is to identify regions of high velocity and also thermal hotspots in the simulation, and then in that process evaluate the efficacy of this HVAC system and suggest improvements. So the idea is to see typically for indoor applications, we want when we say high velocity, that's about 0.25 to zero point 0.5 meters per second. So that sounds a very small amount, but if you're underneath a HVAC system and you're being hit by cold air at zero point 0.2 or zero point 0.5 meters per second, you'll quickly start feeling very cold. And thermal hotspots are regions where there's not enough flow circulation, and that's causing the temperature to just air to just stagnate there. Okay, so with that said, I'll briefly explain the geometry and then start sharing my desktop to show you how I would come about creating this geometry. So instead of just being a presentation, my aim is to show you bits and pieces of how to use this how to use the ANSYS software, which is which I'm most familiar with, and use the ANSYS software to solve this problem. So I can't do the whole thing because this even for an expert, this will take more than an hour to finish. But what I'll try to do is I'll try to point out the key steps. And what I will do is after the session, I will actually share the geometry file and the mesh file with Barry, and when hopefully we can give them out along with the certificates and other presentation slides. So I'll work with him to achieve that. So here is a typical apartment. So I'll show you how we can change a 2D plan, which I showed in the previous slide. So that I actually created the 3D geometry from that 2D plan, this 3D geometry. So I'll show you how I can do it. So let me share my screen. So I'll stop sharing this, or I'll just switch to um, share screen, and then I'll share my entire screen and then share. So you should see my screen now, and this is the image I have, which we saw in the first slide. This is the image of the apartment, and I use the software called SpaceClaim, where you can just start it from ANSYS. Just type SpaceClaim, and it will show up here, and you click on it, and it will open up the this design mode. So I already have this room example, that room already included, but I'll show you how you can quickly bring that in. So you just have that room example as a PD JPG file, and then you can just drag it into here. And when you drag it in, you can choose the location where you can set it. Okay, so that's, and you can click on this icon to view it in the normal mode. So you can rotate it around so that yeah, for example, I can rotate it like this so that I can see this is the outline. So now my task is to create a 3D model out of it. So I can use the sketch mode to start tracing these dimensions. So first thing is I can so let me just draw this line. Say let's just draw this line, and right now it's showing that. So if I look at if I select this line, I'll hide this. So if I select this line, you or if you select this, or so if I draw this line once again, it'll actually tell me the value of that line. The other way is to look at dimensions, create a dimension like this. So now it's saying it's 12.19 millimeters. Our obviously our apartment is much more than that. So what I will do is I will go back and I need to scale this up to realistic proportion. So now what I will do is I'll just do the same thing, but I'll select the length of the room and again set a dimension. So now it's saying this is 25 millimeters. So what I can do is I can scale this up to be about 5 meters. 5 meters. So which is, just set this as 5,000 millimeters. So if I hit enter, what will happen is uh, this will just become a very large line. And what I can then do is I can select this, select once I finish. So now I can scale this out so that the I can scale this out. Also, actually, when I scale it, so there's this option to keep the aspect ratio locked, which means when I scale it, both sides, the aspect ratio will get locked. And I'll also set the transparency to 0 so that I can see this in more detail, and then zoom out and scale it such that I'm close to that value. Okay, so that's my, okay, let's just do that and scale it such that so this is about 5 meters. So that's typical. Now I can start tracing the tracing across this plan. So let's just draw. So let's just draw. So now that this is 5 meters, I can, let's just make this transparency to 30. Now we can, if we have it as 0, we can't, we weren't able to see the trace that we did. So let's just draw like this, and then like this, and then close up the final one. So that's our outside walls represented. Now we need to do the inside wall. So doing each of these will take some time. So but I'll show you how you can do it. So select, if you want to trace this wall, you can create a wall like this, create a wall like this. So these are doors. Sorry, I'm if you have any questions, I'm not able to look at them because I'm focusing on this. But if there are any questions, I'll go back to I'll answer them at a slightly later date. So this is how you can create all the walls. So I'll do a few and then show you. Uh, so these are some of the walls that we have created. In order to fine tune them, what you need to do is you need to zoom in like this, and there's a move tool which you can use to select this and move it up. and now this has stuck out. There's an option to trim it away, and then you can make changes like this. Okay, so it once you get the hang of it, you can, these are just simple sketching tools that are available. So once you have completed tracing these outline, the next step is to go into the design mode and click select, and or sorry, select the 3D mode. Now what will happen is I'll hide this, and then this is our the base of the room, for example. So these rectangles are actually walls. So we actually delete them because we are interested in only the fluid volume. So the walls will actually be a negative, which we don't need. So this is, for example, the fluid volume. So if I switch on the room again, and then maybe this time I'll make the transparency about 60%, and then also I can select this. Yeah, so there we go. We can see it in a slightly better light. So this is how we are tracing the shape of the walls. So that's our, and now to create a 3D volume out of it, so you just simply select the surface and then and click pull, and you pull this up by say 3000 millimeters. That is about 3 meters. So that's the typical height of a room. And if I click transparent, you can actually see through that. So these are actually the walls, and and obviously I've not finished everything, but this is what is, for example, this storage is well defined. So you have this wall and this wall that define the storage room, and then similarly if I had drawn something here and here, that would define the bedroom, things like that. Okay, so that's how we generate the different compartments. Next up, let me show you how to generate. Let me quickly see if there are any questions or something. Yeah, the software has answers, and yeah, good catch. Thanks for answering that, Mike. So now that we have this, I'll show you how we can create some heat sources. For example, in the kitchen, we would probably have a refrigerator. So again, I go to the bottom surface, the ground plane of this, and go to the sketch mode, and I can click. So what I can do is and then I can select a rectangle and create a rectangle like this. Typically, the refrigerator would be about 600 mm deep, and then about 800 mm wide. So that's like a 500-liter refrigerator. Again, there might be a smaller dishwasher, for example. So that's about half a meter and then 300 mm deep. And then there would be maybe a microwave oven, which would again be around 250 deep and then 500. So things like that. You can create simple boxes. Suppose you want a television in the living room. Maybe it's oriented this way. So let's say it's a big television and it's so 55 inches. We can change it to meters, but let's say this is a meter long, and then about usually these televisions are short, are thin these days, but let's say that's 50 or 100 mm thick. Okay, that's how you can create, and maybe there's a desktop in the bedroom, and that's maybe again about 500 millimeter long, and then 250 millimeter wide. So something like this. And if you go to the design mode again, you will see that it has created some surfaces here, 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 and here. So what you can do is you can select pull and extrude them up. So you can say don't merge them with the underlying uh, no, control. Actually, what you need to do is you need to make a copy of these surfaces and then pull them up. So just say each of, you can resize them, but for example, this you can resize it to say 700 what you can do is you can say this is about 800 or 1800 from the bottom, and this surface is about 750 from the bottom. Similarly, you can size all these. So these are your so this is your fluid, and then this is your heat sources. So call this fridge, then call this so sorry, that's sorry, this would be the TV, and then this would be the fridge, this would be say dishwasher or something, and then this would be a desktop. You can do all this, and these will be the source terms. So now what you will see is, let's just change the color for these, and then desktop, go to display, and you can change the color to be violet, and then switch on everything. So we can see these surfaces. Now next step is to do inlets and outlets. I'll quickly show you how you can do that. And usually inlets and outlets are either at the from they're coming from the roof. So if you, for example, if I want to switch on the room, and this time I'll make this zero transparency so that we can see them. So you see these square sections, they are usually the inlets, but for sake of simplicity, I'll assume they are circular inlets. So I can select and set a circular inlet like this, and I'm using a random um, um, so you can just select and then create. I think it's not showing me because of the transparency setting, but you just map these inlets like this, and outlets may be here. So if you click, go to the design mode again and hide this room example, you will see what has happened is okay, you'll see that these have been created at the bottom. There's an easy way to fix that. So let me, okay, there's an easy way to fix that. So select this, and you can go to selection, select the faces of the same area, and I can project these faces onto the surface. Select project and select the surface, and then done. And what has happened is it has projected those inlets to the top. And now what I can do is I can again select faces of the, sorry, coincident faces, and then remove this, and it has selected all the um, faces of the same area. Or I'll show you another way. So hide these, and what I can do is I can do a box selection like this and hide these faces, and then click the fill option to delete them. So now I have my inlets. So again, go back here, faces with the same area, and use the pull option to create like a duct through which the flow will come through. Okay, so that's their inlet duct. So this is how you can refine this further, but this is how the refined example would look like. So I had a few more settings or heat sources, and these are my inlets. I assumed that they are an annulus, so it's actually coming from this ring rather than the whole surface. And these are my so my outlets. So if I go to so these are my outlets. So the outlets are not a ring, but they are these surfaces. So the flow comes in from these inlets, which I'm highlighting here. So these are the inlets from which it's or sorry, these inlets are from where it's coming, and then this outlet is where the flow is going out from. So this is the I'll try to share this geometry with you. Another thing to remember is the the fluid and the solid should be either coincident, or there should be a gap between them, enough gap, so that you can create cells in between. Okay, so that's critical, and otherwise you'll run into trouble with poor quality elements. So once we have this, I'll just show you another thing to check. And what we need to do is we need to use what is called as shade topology. What that is doing is it is identifying which regions um, of these bodies touch, and then it is going to map them for meshing purposes. So this is an important step. Click on shade topology, and then you see this color which is similar to the color we have here. That is basically telling that there's a for example here there's a face here which is connected to this surface and this surface, and same thing at the bottom. So this face and this face, there's appropriate connection between them. So once that is done, next step is to uh, do the mesh, and for that you actually click this button. um, right now I've already clicked this, that's why this is gray. And if you click this button, there'll be an option called watertight geometry workflow. Um, and let me just open SpaceClaim in the background and see if it will show you. But this is the fluent meshing software which gets opened when we click on this button. And here I have this is the workflow that is present. So let me see if I can show you. Yeah, so in here, there's this watertight geometry workflow. If you click on that, what will happen is it will launch Fluent like this with this workflow, where if you clear all these steps, you'll have a nice volume mesh like this. Okay, so I'll show you how we can do that step by step. So first step is to import the geometry. So it already remembers the geometry that I have created. So I just, and then you can change the units if you want. I'll leave it as millimeters. So I'll click update. So what will happen is I have this room HVAC demo, which I showed you, that will come through into the software. Now, next step is to an option to add local sizing. So in real, what you would do is you would want to limit the growth of cells in certain regions. um, right now I don't add it, but that's because I already have constraints with the mesh. So so I'll just skip this. I'll just say I don't want to add any local sizings and click update. Next step is to generate the surface mesh. So what you have to tell it is you have to give it the smallest and the largest size possible. And the requirement for smallest size is it should the smallest size element should resolve the smallest feature of this geometry. So it could either be this thickness of the wall or this inlet section. So right now I have set this as 6 millimeters, and then the maximum size is the biggest size that will get generated, which is 192 millimeters. So that's about 20 centimeters, and this is zero 0.6 centimeters. Okay, and you can, for now you can set these leave these as defaults. So this curvature, what it would do is when you have a curved surface, it will refine that curve. It will have ensure that there is enough resolution of the mesh in that, and the cells per gap will actually resolve this thin region, this wall thickness. It will resolve that properly. I don't have enough time to explain this in detail, but what you can do is if you click on this question mark, it will take you to the help where it will explain this in more detail. There's a help manual which you can use. So click on the generate surface mesh, and that's the surface mesh it has created. So I can, and then I can inspect this in different by different planes. So this is the plane that I have generated. So you can see there are 3 cells here, and let's just hide this. and this is the curved section. Okay. Next step is to explain to this measure what kind of a geometry you're providing. So this is like a multiple choice question, only one correct answer. So in our case, we have fluid and also these heat producing sources like refrigerator. We assume they are solids, or and then so we use the third option. You can use again these. You can go through this question mark and then it'll give a quick help. Um, and in this case, the answer is no for all these. So I'll click describe geometry. And then I have this update boundaries where I have to specify the inlet and the outlet boundary type. So one thing I forgot to mention is when you're doing the geometry, for example here, the way to select these as inlets is to, for example, select a few surfaces and go to groups and click create NS and call this inlet, and then you can select this and select this and call this outlet. Okay, so what you're saying is these are the flow four phases through which flow comes in, and these are the two phases through which the flow goes out. That's and that's what I've specified, and I have a mass flow inlet for the inlet and pressure outlet for the outlet, and click update boundaries, and then I have only one fluid region here. um, so I specify it's just one region and click create regions. Then I have update regions. So it found this closed volume which is called fluid. You can see that is highlighted in green. Then I have my each of these. So let me just, so this is a TV, there's another TV, there's a blender, a desktop, dishwasher, dryer, other things, washing machine, things like that. So I've given like temporary tentative wattage so that I can easily set them when I'm setting up my Fluent simulation. So I'll click update regions, and these are all solids. And then next step is to add a boundary layer. So right now I've just added one. Recommended is 5 or 6. But for actually another step is when it generates the surface mesh, just have a look at the face count. I'm using ANSYS student version, which limits the mesh to about 500,000 cells. So if you have anything above 100 million, you can't really add a lot of 100,000, you can't add more than one layer. That's why I have just one layer, and I'll click update, and then click on next step is to generate the volume mesh. So I use this method called polyhexcore, which will combine these triangles, a few triangles into a hexahedron. So if you see these triangles, let me just identify. So if I select this, 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 so in the mesh generation process, this will get combined into one hexahedron. Okay, so um, let's click generate the volume mesh. So there we go. That's our mesh. And if you go to the console, it has done 464,000 elements. We can go up to 512,000, but I think okay, there was some error.
Hi, Vijay.
Hi, sorry, how long was it
Yes,
on for?
yes, it's uploaded now.
Okay. Were you able to see whatever showing or no?
Yes, I was able to. Then I'm sharing the another slide now, the initial one.
Okay, okay.
Thanks.
But were you able to see my screen?
Yes,
Okay, okay,
thanks.
okay. Sorry about that. So, okay. So can you see my screen? Maybe if you just Barry, if you just message,
Yes,
just speak, uh, I'll know
yes,
that
I can.
something's going on. Yeah. Sorry.
Yes, I can see your screen.
Okay.
Thanks.
So we just have to wait for this process to complete. But in the meantime, I have a mesh that I said I have already done, and what I'll do is I'll just load that up. So if I just open up Fluent, and what I can do is I can read a mesh file. So for example, so if I go to the working directory I have, I can go in there, and so that's my mesh that I created. So I'll click open. Use 4 processes. I have 8 cores actually on my machine, but the student version will allow 4. You don't have to change these options. You just click start, and what that will do is I'll open this in the solution mode. I'll just check. Okay, it doesn't like that the fact that I'm using this, so I'll stop this and close. No. Okay. Are you still with me? Okay. So if I just open up Fluent again, and this time read the mesh, and that's my mesh, and click start. Sorry, I'm rushing this a bit, but hopefully if you watch the recording again, it will make more sense. So we first created the geometry from a simple plan form. Then we generated a mesh in Fluent Meshing. Now I'm in the third step where I'm going to set up the boundary conditions to solve this problem. So I like using this tab graphics console option where I can switch between the console, which is essentially this output of the solver, and then the graphics where I can see the model. So for that, what I'll do is I'll first create the outline. So I'll select the wall and then just show the faces. So that's my wall. Call this mesh faces. Now, next up is to set up the models. So I already have a turbulence model called K omega SST model, which is a good industry standard. We need to specify heat sources. So right now energy is turned off. So, but if we want to specify heat generated by our appliances, we have to switch on the energy equation. I'll say okay. Another thing we need to switch on is gravity, because what happens when you have heat supplied to air, that air will get hot and that hot air will rise because hot air is lighter than colder air, and you need to switch on gravity to capture that dynamic. So and then you need to specify the correct direction the gravity is pointing in. So the gravity is pointing in minus z 9.81, so it's minus 9.8. You don't have to give the units. The units expected are over here. So that's my models done. Next step is to set up the materials. So air is the working fluid, so that we have air in the apartment, so that's the default. So when you have heat, the density of air will change, and the best option for capturing that is this incompressible ideal gas. Okay, and you can leave these as kind of constant and click change create. So that's my materials done. In the next step is the cell zone conditions. So this is where we need to specify some information. So for example, let's look at this TV. So this is saying we assume this is generating 1000 watts of power. So what we need to switch on is the source term, and then we specify an energy source. Okay, and then we set this to be a constant value. So here it's saying it wants information in watts per meter cube. So it's not, if I just give 100, it'll assume that it's 100 watts per meter cube that is being generated. So the best way to check this would be to create what is called as an expression. So cancel this and right click on named expressions and click new. And what you do is, so this is called, let's say TV um, source, and then 100 watts divided by the volume of the TV. So if I go to functions reduction, there will be a volume option, and then it's asking what's the location. So location would be, if you go to location cell zones, so there's this TV. Okay, and that's your value. That's your value. It's 277 kgs per meter per second cube. I'll click OK for this, and then go back to the sources and set this to be 1. And here, instead of a constant, I'll select expression. And then it's saying enter expression, or in the drop down, you see this expression I created, TV source, it's picked that up. So the key thing here is Fluent will only show the expressions which have the units that match. So suppose you have an expression for velocity, which is in meters per second, it won't show up in energy sources because the units don't match, it will not show up. So when you're creating expressions, you need to ensure you have the right. So that's why I had this watts. If I just had it 100, then now Fluent will give me an error because the expression, the units don't match. So you can create named expressions similarly for all the other sources um, and say dishwasher, desktop, and all that. So I use some. These are slightly higher on the higher side. In reality, they'll be about half of what you actually have here. So that's how you set up your heat sources. Now you need to specify your cooling flow, so the air conditioned flow. So you have this inlet. Again, I have 50 LPS, which is like short form for liters per second. So I need to convert that into a mass flow rate. So to convert that into mass flow rate, I need to specify the temperature with which this cold air is coming. Usually, right now this is in Kelvin. I can change this to, I can change the units to be um, Celsius. So if I click on T, it'll take me to temperature. So I can change from Kelvin to Celsius. And now you see that the temperature has changed to Celsius. So set this as 13 degrees. Okay. So that's what I've done is I've set this to be 13 degrees. And now I need to specify the mass flow rate such that it is 50 liters per second. Again, I'll create a new expression and so call this inlet mass flow. Just check if I'm still here. Yeah, I'm still here. And then so if I have 50 liters per second, so that is 50 into 0.001 meter cube per second, right? So 1 liter is one, or 1000 liters is 1 meter cube per second. So that's why I multiplied with that 001. So now that is, we need to then get kgs per second, which is the mass flow rate. So to do that, we multiply with density 1.225 kgs per meter cube. Okay, so that's my density. And if I click refresh value, it's telling me it's some kgs per second. Okay, so I'll click OK to that and go back here and select expression, or you can just see this inlet mass flow. And we have 10. Ideally, we should, the density at 13 degrees Celsius is higher than 1.225, but I've just put that as a number to show you how you set up your inlet condition. Okay, So that's my inlet. Then I have my outlet, and again leave the backflow temperature as default. So when you have the outlet condition, you assume that it's exiting to atmosphere. So that's why we set this to be 0 gauge pressure. You can leave these other settings as default. This is where you change the turbulence. For example, if you know the diameter, you can specify the intensity and length scale to give the size of eddies that get generated. Usually this 5% turbulent intensity is a good number. So I'll click apply and close. So I have set my heat sources. I've set my inlets, outlets. These walls, I'll assume they are adiabatic, which means they don't lose any heat to the outside. And I'll also show one more thing where I'll show you how to copy from one cell zone to other cell zones. So for argument's sake, let's say all of these cell zones have the same heat source. So which I selected. What I can do is I can copy from this cell zone to all these zones. Click copy and say OK. And if I open this oven, for example, okay, the source term has not, yeah, it's a good option to check for source terms. Okay, fine. For some reason it didn't go through. Maybe I didn't say okay. So say okay, apply. Maybe I switched off to something else without applying. So if I select now, the source terms are there. Let's repeat the process. Click copy and then select. So here it will only find relevant like solid cell zones. It will not show you any fluid cell zone. So click copy and say okay and close. And then now you see the source term and you see that it has picked up that TV source even for this oven. So instead of doing it 4-5 times or 7-8 times here, I can use that copy. So I think with this, I have most of my setup done. I can start running this simulation, but I'll do a couple of other things. First thing is I'll create a flux report of mass flow rate. And what this does is if I select all the boundaries, I can look at mass imbalance. So mass imbalance is basically the difference between the flow coming into the from the inlets and going out of the outlets. There should be a balance for us to determine that the flow is converged. So do the same thing where you go to flux report and this time heat transfer. So there's a lot of heat being generated or brought into the system. We need the all of it to go out mostly to the outlets. So this is heat imbalance. Okay, click OK. So these two help us track the state of convergence, and then I think I'm good to go. So let me just save this. Also, make sure you save this. So let's just create a new folder, version 2, and then just save it in there so that I don't overwrite what was there in the previous one. So once that is done, I will initialize, and you can use the default option to initialize, so which is called the hybrid initialization, and that hybrid initialization will basically, for example, let's just look at contours of temperature, let's say, on the walls. So that's our temperature contour where it's showing 13 degrees everywhere because that's the inlet condition. But now let's run this for a little while. For now, you can use the default settings here where we use like a automatic timescale factor and click calculate. Sorry, you need to specify say 100 iterations and click calculate. So it'll start calculating and then it'll show you the residuals, it'll show you the mass imbalance and heat imbalance. Let this run for a little while and I'll go back to the presentation. So if I go to stop sharing and sorry, Mr. Berry, could you share the share the
The previous
presentation
slide.
once again? Yeah, sorry.
One moment.
Also, thanks, Kelvin, for your help. Yeah, thanks again, Barry, for showing uh, showing this again. And so what we have covered so far is so this is the CFD simulation methodology. So we created the fluid domain, we created the mesh, we chose the appropriate models, the correct boundary conditions, and the solver settings. And we are now solving this iteratively, and then we need to visualize the flow field by plotting the contours, vectors, etc. And if you have any experimental data, you can come check the efficacy of this CFD model. So usually what you will see is you might find that when you run this till convergence and look at the contours, you might see it's either too hot or too cold. If it's too hot, it means the flow rate is not enough to capture all the heat and take it away from the room. And if it's too cold, it means you're pushing too much cold air. So in the first scenario, you're going to be too hot, you are going to be sweating, and you need to have more capacity. And in the other case, if you're pushing so much more cold flow, you're wasting energy, because obviously you might know that using AC and all that will cost a lot of energy. So you're unnecessarily uh, wasting a lot of energy, and you're in fact contributing to the global warming, because if even though you use a AC system to cool the air inside your apartment, overall, and because it's not 100% efficient, it actually creates it creates more heat in the process. And which means switching on the air condition is bad for the environment overall. And a good question, Dominic. You can vary it with the time of the day. You can change the ambient conditions. You can also, in this case, I've not added any heat radiation. Usually there'll be windows, and through windows, you'll have sunlight coming in, and that will also heat up the room. It's like the
Hi, Vijay. Hi, Vijay. Apologies, everyone. Just a moment while I'm trying to get him back. Thank you.
Sorry, everyone. I think I just went off. Yeah, there's some connectivity issue. Hopefully,
No
can
problem.
you hear me?
Thanks,
Okay.
Vijay.
Yeah, sorry. Yeah, there was some connectivity issue.
Yeah.
But yeah, I'm back. Um, so yeah, we've mostly covered all these, the watertight meshing workflow, the solver setup, and everything. So the final thing to check is how to look at the contours. So these were the solution monitors. So I looked at the mass imbalance and the heat imbalance. And finally, you can go to the contours section and create some planes and visualize the flow patterns. So here is an example where I find these hotspots, where these are the regions where the velocity is higher, about zero point 0.4, zero point 0.5 meters per second. And these dark blue regions are where the flow is almost stagnant. So you don't want it to be completely stagnant, which means the air is not um, going from that room. and you don't want it to be red, which means there's a big draft that you feel when you're walking in that region. Okay, so you ideally want it to be light blue or green to in this scale. So from 0 to zero point 0.5, it should be either in the light blue slash green. Maybe orange is okay, but if you start seeing more red, it means that's not the ideal place to be. What the way to fix this is to look at different locations of the inlets to see if you can get this to be more uniform. Next up is to look at the temperature contours. So here you see again 13 is your supply flow rate. So blue is 13, and then 23 is the hottest you see. 23 degrees Celsius is not that bad, and that's because I did a couple of iterations to size this HVAC system. First time you um, once first time you do it, you might find that you're seeing a lot of red or a lot of blue. So you have to tweak the flow rate or tweak the source information, heat source information to get a result like this. Okay, so and then we can also plot the velocity streamlines, and what this is showing is this is showing where if you see these jet streams going vertically down, it means that they are actually reaching the ground, like where we are, whereas these are kind of mixing with each other, and they're the streamlines are kind of chaotic. So we should ideally aim to have jets which are coming down and then spreading across. That will mean that that has the most effective mixing between the hot air and the cold air. So we can visualize these things in CFD as well. And this is colored with temperature. So you can see this region is hotter than these regions. So you see this orangish hue, which means the air is getting hotter here. And this is actually the region where of the kitchen where I had a lot of heat sources. Okay, so basically that's how you can visualize what's happening in the flow. So just to summarize, I went through a brief introduction on how to uh, conduct a CFD analysis for a HVAC system of an apartment. So we visualized, I went through how to set up the problem and generate a geometry, generate a mesh, set up the simulation, run it. And I didn't show you how to post-process it, but if you look for post-processing ANSYS Fluent simulations online, you will find quite a few videos that would explain this in a lot of detail. And the idea of using this software is to evaluate the efficacy of this HVAC system in ventilating the space. So we saw which regions could have high velocities, and then which regions could have high temperatures. And understanding the flow patterns, you can come up with ideas of specifying or move around the inlets and outlets so that you have a more uniform velocity. And the other thing is this there's a suggestion that came to me after analyzing the flow field, is to set the exhaust in the kitchen, because if I go back to the streamlines, you see this hot air that's actually going into other rooms from the kitchen. What if you had an exhaust there? All the hot air will just escape out from that exhaust instead of coming into the room. So if it's 23 degrees, it's not that bad, but if it was 45 degrees or so, you would be better placed to have an exhaust there. Okay, so the other advantage of the CFD simulations, it's more cost effective than conducting experimental analysis. If you wanted to do an experimental analysis, you would have to create a scaled version of this model, maybe 1:10 scale, and then start introducing hot air, cold air, and do that. So CFD gives you a lot of advantage in this time. That's a good question, Dominic. How long will it take to mix in the air? There's a formula to compute what is called as age of air. If you search again online, you can find this formula. You can use that to get that answer. And you can have a color contour where you can have blue regions which indicate good mixing and red regions which indicate poor mixing. And Kelvin, for your question, what resources do I recommend for heat source rating, flow rate? Best is to look at some examples of apartment HVAC systems. There might be some designs that are like typical designs that are provided. But yeah, that's another nice place. Professional certificate in heating, ventilation, and air conditioning systems. So I think I'm out of time, but thanks again for being patient and bearing with me when I had those couple of hiccups. Hopefully it recorded well, and you can get access to the recording once it finishes.
Yeah. Thank you so much, Vijay, and thanks everyone
Thank
for
you.
joining. Yeah, just quickly running just few last slides. So these are just some of our upcoming programs. So if you are interested in checking what we are offering, so you can always just go on EIT website and check under course schedules just to see our upcoming programs. And then Munashi, we actually have a professional certificate in heating and ventilation and air conditioning. I just shared the link to everyone to read more about it. So just feel free to reach out if there's any questions. You can always just send us an email to our webinars, and then we will assist you. Yeah, these are some of our upcoming webinars. So we have low voltage design, maximum demand. And then if you are interested in attending our EIT Virtual Open Week, it's happening from the 23rd to the 26th of October. So should you like to know more about our EIT, our offerings online or on campus, just ensure that you sign up for the event. It will be happening 100% online. And for just I've mentioned in the beginning that I'll be sharing a QR code in order to record your certificate of attendance. So if you can just quickly scan the QR code, or I will just quickly post this link here. So if you can just follow that link in order to complete the short survey form. Please note that you've got until Sunday, the 8th of October. If you do it after that, unfortunately, we will not be able to provide you with the certificate of attendance. So just do it as soon as you can. I just posted a link just now, so just use that link to request your certificate, or you can scan the QR code in order to complete the form. And yeah, that's it from my end. Thanks everyone, and just always feel free to let us know if you have any suggestions, if you have any feedback. Just always make use of this email address to share your experience with us. And yeah, thank you so much. Have a great day further.
Thank you, everyone.
Thanks, Vijay. Have a great one.
You too.
Cheers.
Thanks, Berry. Thank you.
Bye.
Bye.